episode comes to you. This lesson comes to you from the Academic Resource Center, brought to you by the letter alpha and the number 1/10. Today's lecture comes in two parts, but I said that last time and then I lost count. So the first part is about alpha, and the second part is about ANOVAs. And this is the test we're actually going to be doing. But first, let me explain to you why. So alpha is a Greek letter, and in statistics, it represents the chance that you could make a type 1 error. In statistical terms, a type 1 error is if you reject the null when the null is in fact true. In regular English, that means you think you got a result from your test, but actually you didn't. So a standard value for alpha is 0.05. That means there's a 5% chance that we make a type 1 error, but there's a 95% chance that we did everything right. Okay, now bringing power into this from last time. If an experiment doesn't have a lot of power, which is usually dependent on the number of subjects you have and how far apart your groups of data are or aren't, we can adjust alpha to increase power. In this case, I would change alpha to 0.1. It's slightly less conservative, but that's a good thing because for you, I want to make sure we get results and we don't just do all this math and not get any significant results. So with an alpha of 0.1, we can run a t-test. But we can't just run one t-test because you have 7 different samples. So we have to compare the original recipe to all 6 of the replacement recipes. And there's an alpha of 0.1 for each of those. So 0.1 times 6 is 0.6. That means all of a sudden there's a 60% chance that we're making a type 1 error. And that's awfully high. Fortunately for us, there is another type of test we can use. The F test, or ANOVA, which stands for Analysis of Variance, is a test that will run all 6 comparisons simultaneously. And our alpha will stay at a low 0.05 or 0.1. However, what ANOVA doesn't do is it doesn't tell us between which groups there are significant differences. It only tells us if there is or isn't a significant difference. So then we have to run a post hoc test afterwards, which you know from the Latin means after the fact. And that one will tell us between which groups there are actually significant results. But that's the last step we have to worry about. Analysis of variance, which is abbreviated ANOVA and is also known as the F test because in the end we're trying to find F obtained. Unlike z-tests and t-tests, the ANOVA doesn't compare means, it compares variances. The ANOVA is going to compare the variances between your groups to the variances within your groups. Variance is defined as standard deviation squared, and if you remember from the first lecture, standard deviation is just a measure of how much the raw scores deviate from the mean. So essentially, variance talks about how spread out your raw data is going to be. And over here, I'm going to draw you a picture. So this first lumpy normal curve is a high variance and a high standard deviation. So there's a lot of variability, as you can see. The second one is a medium variance and a medium standard deviation, and the third one is a low variance or low standard deviation. So now you know what they look like. Alright, when talking about samples, we write standard deviation as S, not as sigma like we do with populations. Accordingly, variability is then S squared because, like I said, it's defined as standard deviation squared. Alright, the ANOVA test assumes that your independent variable is going to have an effect on your dependent variable, and it's going to be displayed by showing a greater variance between your groups than within your groups. So if we were to write this as a formula, it would be variance plus the effect of the independent variable over just the regular variance. And we're trying to measure the effect of the independent variable right here. So how high your f needs to be depends on the number of subjects you have and the number of groups they're divided into. So as I mentioned before, the f obtained for the ANOVA is the ratio of the variance between the groups over the variance within the groups. The variance between groups, then, is defined as sums of squares between groups over degrees of freedom between groups. And degrees of freedom between groups is equal to k minus 1, and k is the number of groups. In the same way, the variance within groups is the sums of squares within groups divided by the degrees of freedom within groups. And the degrees of freedom within groups is n minus k, and n is your total number of participants, and again, k is the number of groups you have. The formulas for sums of squares differ a little bit, but we also need to find the sums of squares total, which you'll see is exactly what I showed you the other day in the t-test. The sum of x squared minus the sum of x squared all over n. When it comes to figuring out these ANOVAs, I always draw this chart. Across the top, I put sums of squares, degrees of freedom, variance, and then f. And along the side, I do between, within, and total. And this is just going to set me up to check my work periodically, and it'll lead me right straight into the answer. So that concludes today's video. Once I get your data, I'll make another video on running the Anova test with it. What's that thing called? I still remember.